In this video, we're going to be doing a Unit 8 Fluids FRQ. A large vertical tank contains two immiscible fluids. The top layer is oil with a density of PO and a height of HO. The bottom layer is water with density of water and height of water, where density of water is greater than the density O. The tank is open to the atmosphere at the top. At the bottom of the tank, a horizontal pipe of cross-sectional area A1 is attached. The pipe narrows to a nozzle area 2 before exiting into the air. A rectangular block of density P rho B floats at the interface between the oil and the water, partially submerged in both fluids. The block has a total volume V and a cross-sectional area of A, and it's free to move horizontally. As the fluid exits the nozzle, it forms a horizontal jet that strikes the block, causing it to accelerate across the surface. The block experiences negligible friction. So we're going to assume that the fluids are incompressible and non-viscous, that the flow is steady, and that the tank is sufficiently large that the surface speeds are negligible. The fluid exits the nozzle at atmospheric pressure. So this is our diagram here. We have our oil here at the top. This is the atmosphere, which is the air up here. We have oil at the top, and then we have water at the bottom, and we have the block where it's split along that line. And our different definitions of height here, and we have our nozzle and a jet. So for our first question, we're asked to derive an expression for the absolute pressure at the bottom of the tank in terms of these variables. So this is pressure at the bottom. We have layered fluids. And what that means is that for each layer, pressure is added. So pressure is equal to pressure at the top plus rho GH. So we have two layers. At the top, we have the pressure is equal to the atmospheric, and then if you add the oil, then you have pressure is equal to pressure atmospheric plus P initial, GH initial. And then water, we have, this is rho water, density of water, GH water. So this part is going to be the top, this is the oil, and this is the water. So this is how we get our answer. You have to account for each pressure. You have to account for each layer. So now for part B, we're asked what is the exit speed using Bernoulli's equation. Starting from Bernoulli's equation, derive an expression for the exit speed V2 of the fluid at the nozzle. Your derivation must correctly account for pressure contributions from both fluid layers. So we're finding the exit speed V2. So we're going to use Bernoulli across two fluids. So first, we're going to choose 2 points. Point 1 is going to be the top surface, and then point 2 is going to be the nozzle exit. So the equation will be pressure 1 plus 1/2 rho V1 squared plus rho GV GY, which is your height 1, which is Y is going to be your height. And this is equal to P2 plus 1/2 rho V2 squared plus rho GY2. So at our surface, we have our pressure is equal to the atmospheric. V1 is approximately going to be 0 because we mentioned that we had negligible friction, and also we said that the speed was going to be negligible. Y1 is also equal to 0. When you're at the exit, P2 is equal to the atmospheric. Y2 is equal to negative H initial plus H water, and the fluid moving is water. The density of that is equal to rho water. So now we can substitute these in. Your atmospheric is equal to atmospheric plus 1/2 rho water V2 squared minus rho initial GH initial minus rho water GH water. Now we can solve. We have 1/2 rho water V2 squared plus rho initial GH initial plus rho water GH water. This is V2 squared plus 2 over rho water. Rho initial GH initial plus rho water GH water. And now all you do here is you just take the root of both sides. That cancels out, and you get V2 is equal to the root of 2 times G rho initial over rho water times H initial plus H of water. So that's your answer for V2. Now for our next question, we're asked to use the continuity equation and to determine an expression for the speed V1 in the wider section of the pipe in terms of A1, A2, and V2. So we can see that in the wider section, it's slightly larger, and then it kind of levels off to A2 at a smaller cross-sectional area because it's going to be constricting the water. So what is our continuity equation? We have conservation of masses. So A1 times V1 is equal to A2 times V2. We want A1, so V1 is equal to A2 over A1 times V2. So that's going to be how we can solve for V1. For part D, we're asked, we have the situation that the block floats at the interface such that V water is submerged in water and volume O is submerged in oil. Derive an expression relating the variables. So what we're going to do is we have buoyancy in two fluids. Buoyancy in two fluids. So we can draw the forces. So right now on our block, what we have is that we have an upward force of force buoyant water, and we also have upward force of force buoyant oil. Force buoyant oil. And we can set them equal to different things. Force buoyant oil. So this is equal to rho oil GV initial, and then this is equal to rho water GV water. Write that up there too. Rho oil GV oil. So then downward we have, acting at the center of mass, is the weight force, which is equal to mass times gravity, which you can replace as the density of water times volume times gravity. So now we can apply Newton's second law. We're at vertical equilibrium, so our summation of our vertical forces is equal to 0. In our upward direction and to the right is our positive. So we have our force buoyant water is upward, and our force buoyant O is also upward, and only our weight force is acting downward, so that's going to be negative. Now, all we have to do is to substitute in. So we wrote our equivalencies earlier. That's density of water, GVW, plus density O, GV oil, which is going to be equal to density of the block, GV. So that is going to be our final expression. After we cancel out our G on all sides, we have G. So we can write this as density of the water, V water, plus density O, VO, which is equal to density of the block, V. You could also rewrite this using a different expression for VO. So you could say that VO is equal to your V minus your VW. So this would be VW is equal to V times density of the block minus density of the oil divided by density of the water minus density of the oil. So this could also be acceptable as well. Now for part E, we're asked the force from the jet and the block acceleration. So the jet strikes the block and brings the fluid to rest horizontally. Derive an expression for the force exerted by the jet on the block. So force from jet to acceleration. Part 1, we are finding the momentum flux. So your mass flow rate is going to be M is equal to the density times A2, V2. And now you have a momentum change. Say P change. But actually, let's just write that out because you have other P's here. You have rho and you have P for pressure. So our water is going to go from water V changes. So it goes from V2 to 0. So F is equal to M delta V. F can be rewritten as density of water A2 V2 times V2. So your final force would be F is equal to density of water A2 V2 squared. So that's your final expression. Now for our second part, we're asked, what is the force exerted by the jet on the block? So we're asked, what is the acceleration of the block? So you're going to apply Newton's second law in the horizontal direction. So that means the summation of your horizontal forces is equal to ma. So force is equal to mass times acceleration. We know mass is going to be density of the block times your volume, and that's A. So what we want is to solve for A though. So A is going to be equal to our force divided by our density of the block times V. And we can rewrite this as A is equal to the density of the water, A2 V2 squared, over density of the block times V. Because we can substitute in our answer for what the force is from the previous question. So we have that F. That's how we get our A. Now for part F, we're asked in the scenario that water is slowly drained from the tank so that your height of the water decreases while the height of the oil remains the same. So for each of the, and this is because the oil and the water don't mix. So for each of the following quantities, state whether it increases, decreases, or remains the same and justify your answer. So this is all for questions for F. So first we're asked, how does the exit speed change? So for exit speed, this can be represented as V2, and we already found V2, which was this expression over here. So we're going to examine V2, and we see that if we decrease the height of the water, that means that V2 is also going to decrease because they're directly related. Now, what about our force? What equation is our force? So we see that we just found our equation for our force, which is this equation right here. So we see that if our force decreases, or if we see that V2 decreases, that means that our force is going to decrease because it's directly related. And then for part 3, we're asked, what is the fraction of the block submerged in water? So 3. Fraction submerged in water. So we know that the volume of the water is equal to the volume times the density of the block minus the density of the O minus density of the water minus density O. So we can see that there is no height of the water and there is no height of the oil. So for 3, we can say it stays the same. The fraction submerged in the water stays the same, but this is as long as the block remains at the interface and not touching the bottom.